Hi, this is Dr. Ann O'Connor. Welcome to Pathways to Chemistry. Here we're going to look at the titration of a weak base by a strong acid. So we're told that we have 25 milliliters of 0.1 molar ammonia being titrated with 0.1 molar hydrochloric acid. So we're asked, what is the pH after the addition of the following volumes of acids? So in part A, we want to know the pH of the solution before any added acid. So let's go ahead and do this part. Let's write the equation. We have ammonia in water, and that's in equilibrium with hydroxide ion and ammonium. So this is just simply an equilibrium problem. So we can set up our table: initial concentration, change in concentration, and equilibrium concentration. So our initial concentration of ammonia is 0.1 molar. And of course, 0 hydroxide and 0 ammonium ion. So our ammonia concentration is going to decrease by some concentration X, while our ammonium and hydroxide ion increase by some concentration X. So then we have an equilibrium, 0.1 minus X, and so on. I should have given KB for this in the problem, but KB is 1.8 times 10 to the negative 5. That's for ammonia. So let's go ahead and set up our expression for KB. So that's 1.8 times 10 to the negative 5 is equal to x squared over 0.1 minus x. We're going to make an assumption that 0.1 minus x is approximately equal to 0.1. That means that the amount x is very small, it's negligible. We'll check the assumption in a minute. So that means that this will simplify to 1.8 times 10 to the negative 5 equal to x squared over 0.1. So here we solve for x, and we find that x is equal to 0.0013 molar. And of course, x is equal to the hydroxide ion concentration. So now I just need to find the pH. So I'm going to just find the pOH, which will be the negative log of the hydroxide ion concentration, which is 0.0013 molar. And that gives us 2.87. And then I can use the fact that 14 minus the pOH, which is 2.87, equals the pH, and this is 11.13. So what I'm going to do over here is start a table because they want us to sketch the titration curve for this. So let's start our table up here. I'll use a different color. And so we want the volume and of course the pH. So this is the volume of added titrant. So this is 0 milliliters, and our pH is 11.13. So that takes care of part A. What I like to do when doing these types of problems is find the equivalence point volume. So let's go ahead and do that. And then that way we know where we are in parts B, C, D, and E. So what we have is we have a 1:1 ratio of ammonia to hydrochloric acid. So at the equivalence point, the moles of hydrochloric acid used are going to equal the moles of ammonia reacted. Let's see, we have 25 milliliters of 0.1 molar ammonia, so that's 0.025 liters times 0.1 moles per liter, and that gives us 0.0025 moles of ammonia that's going to react. At the equivalence point, the moles of ammonia will equal the moles of hydrochloric acid. So that's 0.0025 moles of HCl. So now all we need to do is find the volume from that. So we have the number of moles and we have the concentration. So as we know, molarity is equal to moles over volume, and volume then is going to be equal to moles over the molarity. And so we have 0.0025 moles of HCl, and divide that by the molarity. That's 0.1 moles per liter. So the volume is going to be 0.025 liters, or 25 milliliters. So equivalence point volume is here in part D, and that's 25 milliliters. Let's go on to part B. We know we're before the equivalence point, and the same with part C. We're before the equivalence point. So we'll go on to part B after the addition of 5 milliliters of hydrochloric acid. So what we have is, here's our equation. We have our ammonia plus hydronium ion, and it gives us ammonium ion and water. What we have here, after the addition of the acid, we have a buffer situation. What we need to do is figure out the number of moles of ammonia and ammonium ion in solution. So in order to do that, what we're going to need here is, we have our KB. KB is equal to 1.8 times 10 to the negative 5. We need to find the moles of acid that added, so moles of added hydronium ion. And so we have 5 milliliters, which is 0.005 liters. Multiply that by its molarity, and that'll give us the number of moles of acid that's added to solution. 0.005 moles of hydronium ion, or acid. And then from that, we need to determine how much ammonium ion is produced, and then how much ammonia remains. So what we need to do is subtract from the number of moles of ammonia. So from part A, the number of moles of ammonia was 0.0025. So the moles of ammonia left will be 0.0025 minus 0.0005. Okay, so it's going to be 0.002. So that's the number of moles of ammonia left. And the number of moles of ammonium produced would be equal to 0.005 moles. Okay, so now we're all set to use the Henderson-Hasselbalch equation. What we do need is the pKa. Now what we have is Kb from part 1, which is 1.85 times 10 to the negative 5. And let's see, Ka will be 1.0 times 10 to the negative 14 divided by 1.85 times 10 to the negative 5, and that is going to give us 5.6 times 10 to the negative 10. And so this is Ka, and pKa will be the negative log of that, and we end up with a pKa of 9.26. Now we can determine the pH using the Henderson-Hasselbalch equation. So pH is pKa plus the log, and in this case here, it's going to be the ammonia concentration over the ammonium ion concentration. Now, notice we just have moles here. All we had to determine were the number of moles of both ammonia and ammonium ion. Volumes cancel out. So I can just go ahead then, and we have 9.26 plus log of, first we need the ammonia, the moles of ammonia left, so that's right here, 0.002, and then the moles of ammonium ion produced, which is 0.0005 moles. And so our pH then is equal to 9.86. So let's go over here. So after 5 milliliters, we have a pH of 9.86. So that's after 5 milliliters. Bring that over so you can see it. And the pH is 9.86. Okay, let's go on to part C. In part C, we want to know the pH after the addition of 12.5 milliliters. Now, it's a good thing we determined our equivalence point volume in part 1, because we know our equivalence point volume is 25 milliliters. So that means after 12.5 milliliters has been added, we're at the halfway point. So at the midpoint, or halfway through the titration, here's what it looks like. The concentration of ammonia is going to equal the concentration of the ammonium ion. Let's take a look here at the Henderson-Hasselbalch equation first, okay? So we have the concentration of ammonia divided by the concentration of ammonium ion. So if these are equal, then what we have is log of 1, and log 1 equals 0. So at this point, pH is equal to pKa, which of course is equal to 9.26. So that's halfway through the titration. Now we have to determine the pH at the equivalence point, and that's when all of the base has been reacted with the acids. Okay, so at the equivalence point, what we need to do is determine the concentration of ammonium ion, because all of the ammonia now has been reacted. Okay, let's go ahead and determine that. And so what we have is 0.1 molar ammonia. And I'll just put that as moles per liter. Okay. And so we have 25 milliliters, or 0.025 liters. Okay. And then we have to realize that we have a 1-to-1 mole ratio of ammonia to ammonium ion. And then we just go ahead and divide all this by the total volume, which is 50 milliliters, or 0.05 liters. And once we do that, we end up with 0.05 molar ammonium ion. So now we can set up our equilibrium table here. So we have ammonium ion plus water, and that's in equilibrium with hydronium ion plus ammonia. So let's set up our initial change in equilibrium concentrations. So we just calculated the concentration of ammonium ion as 0.05 molar, and that's going to decrease by some amount x, and of course hydronium ion and ammonia will increase by some concentration x, and then here we can write our equilibrium concentrations. Now what we need is Ka, and we determined Ka in a previous part. So Ka is 5.6 times 10 to the negative 10 very small equilibrium constant. And we can go ahead and set up our expression. So we have Ka is 5.6 times 10 to the negative 10, which is equal to x squared over 0.050 minus x. X is definitely going to be negligible here, so what we can do is simplify this to be x squared over 0.05. Solve for x, and we get x equal to, of course, our hydronium ion concentration, and that is equal to 5.3 times 10 to the negative 6 molar. So then our pH is equal to the negative log of 5.3 times 10 to the negative 6 molar, and that should be 5.28. So after 25 milliliters is added at the equivalence point, our pH is 5.28. So let's see what we have here. So after 25 milliliters, the pH is 5.28. So after the addition of 30 milliliters, the pH only depends on the excess hydronium ion concentration. We have to figure out how much acid is in 30 milliliters, or how much hydronium ions. So we have the acid was 0.1 molar. Multiply that by 0.03 liters, and we end up with 0.003 moles of hydronium ion. We know that 0.0025 moles of hydronium ion reacted with the ammonia. So let's find the difference here. So our hydronium ion concentration then is just going to be 0.003 moles minus the 0.0025 moles. That's going to give us 5 times 10 to the negative 4 moles of acid. And then, of course, we have to divide that by the total volume, which would be 30 plus the original 25 milliliters. So that's going to be 55 milliliters. So we have 5.00 times 10 to the negative 4 moles of acid divided by 0.055 liters. And that's going to give us 0.009 molar. And of course our pH then will be the negative log of the hydronium ion concentration. Negative log of 0.009 is 2.04. So after the addition of 30 milliliters, our pH is 2.04. From this data, what we can do is we can go ahead and plot our basic titration curve. So of course, we started off with a basic solution, and so we're going to see the pH jump here, and then of course move down. So remember, the halfway point of the titration, okay, which would be somewhere right about here, this is where the pH equals pKa. And of course, here we have our equivalence point after 25 milliliters. So what's important is we have several basic regions in this curve. Let me get that up there to show 0. We have a buffer situation here. In this region here, we have a buffer situation at the halfway point of the titration. The pH is equal to pKa. And then we have our equivalence point, and then the region after the equivalence point, which is just due to excess acid.